Hello, calculus fans. Okay, so we've got a couple of error bounds for the trapezoidal and midpoint rules. We have a theorem that tells us how big the error bound might be before we even start. So let's suppose that our f double prime is less than or equal to k. So we have some upper bound on what the second derivative is. And let's say that e sub t and e sub m are the errors in the trapezoidal and midpoint rules. Then there's a formula that says that the error in the trapezoid rule is no bigger than k times b minus a cubed all over 12n squared. Remember that n is the number of subintervals that we use. And then the error on the midpoint rule is smaller than k times b minus a cubed over 24n squared. We're not going to do anything to show why these are true. These come from a branch of mathematics called numerical analysis. We're just going to use these to try to compute some error bounds. All right, so let's go ahead and apply this to the integral that we've been working with. So f of x is going to be 1 over x squared. If we take a derivative, we'll get negative 2x cubed. And then a second derivative will get us 6 over x to the fourth. Now one thing to note is that when x is between 2 and 3, which is all that we care about since those are the bounds on the integral, 1 over x to the fourth is no bigger than 2 to the fourth. Right? If we pick a bigger value of x, then that fraction actually gets smaller. So this enables us to create a bound on our second derivative. So f double prime of x in absolute value is equal to the absolute value of 6 over x to the fourth. And now that's smaller than 6 over 2 to the fourth, which we can simplify to 3/8. So if we go ahead and choose k equals 3/8, a equals 2, and b equals 3, then we can plug these into our error bound formulas, and we get the error bound on the trapezoid rule is no bigger than 3/8 times 3 minus 2 cubed all over 12 times 5 squared. Remember, we used n equals 5. And then if we plug everything into the midpoint rule error formula, we get something a little bit smaller. If you go back to the previous slide and look at the actual errors that we computed, they were smaller than these error bounds, and that's what we expect. So this theorem tells us what we can expect to get, and the actual errors that we got were smaller than these bounds. The bounds tell us how big the errors could possibly be, but then the actual errors may be smaller. Right, so that's what we have here. So the actual errors are smaller than these error bounds. Okay, that's all for now.